304. Let's do it. A steel plate of thickness h has the shape of a square whose side length equals any figure given 1.79. This thing. So it's a steel plate, length L and L. Okay. With h much less than L. What is h, by the way? Of thickness. Okay, fine. The plate is rigidly fixed to a vertical axle, which is rotated with a constant acceleration. Okay, beta. Fine. Find the deflection, assuming the sagging to be constant. So this is our deflection, right? So in the rotating reference frame, just got omega square r thing happening over there. Oh, this is going to be hard because this is like the force is just varying with respect to that. That's the problematic thing. I wonder if there's some way to. Yeah, I don't think there is. Think about it. Is there some way you can just figure out what that torque is going to be in the rotating reference frame? I don't know. I don't know. But at least it's. Yes, like, okay, there's omega square r. Moreover, there's also this other term that you have to look for. Uh-oh. This doesn't look good. This doesn't look good. Or you could just do the analysis of a single element, so just alpha r in this direction and then omega square r in this direction. Okay. So like omega square r, for that you would need some normal tension, which is going to cause. Oh, okay. That's weird. So you do need some normal tension for that, huh? This is much different than what I thought it would be. So usually you have normal tension. Of course you have that, but then its net effect is just 0, and now it's not 0 anymore. So then can we still use the same equation? Can we use tau equal to IA Young's modulus upon radius of curvature? I think we can, right? Yeah, we can, because right. You can just think of the normal force. So the force required to keep it orbiting, right? What I'm saying, keep it in the circular motion. So omega square r and omega square r, right? You can think of that as being an additional pair of forces. So like additional bunch of small forces that you have to add up on that line. Which means you can just, use superposition of strains and everything, and yeah, there you go. You can still do the same thing. You can still do the same thing. You can still apply our equation, right? Yeah. Because, okay, your element, like it's getting bent because of some kind of moment, and it's like this. But if you just stretch it, yeah, if you stretch it, wait, okay, stretching it might change everything. No, it won't. Why would it? It will slightly shift this, but then it just slide, right? It's gonna stretch this a bit. Okay, it's like this, but it's not that big of a change, right? So the radius of curvature is still the same thing, I guess. Yeah, it's almost the same thing as before, just there's extra strain in the normal direction. So, yep. Okay, let's do it. So this will be our x. Okay, this is our x. Fine. Then you have omega square r, that's the normal force, and then there's alpha r. So this needs omega square r in this direction. So you have to put that force in there. But that's not what we look for. We want to look for the torque, right? Yeah. Or maybe we should just go for the rotating reference frame. I guess so. So then in the rotating reference frame, there's a pseudo acceleration of omega square r in this direction, right? Okay, and omega square r pseudo force in that direction. And then you got mr alpha in the opposite direction of whichever it is like rotating with. So this is mr alpha for each of these, right? Okay, and you want the net torque on this thing. Oh god, this is going to be not so good. It's like this thing. If this is right, it's like summation of mi alpha, and then like okay, mr alpha supposed to be xi, right? Okay, xi. But then there's also the this thing that you have this xo. Okay, xi. That is the force. This is the force. Then you want this times arm length to be our torque, right? Okay. So you want this summation. Okay, interesting. Now, what is okay? I would like to convert this into an integral, but let's see if there's something I can do with it. So, okay, this can be written as summation of well, this thing. So that's just like the inertia of if you had all of this mass at this point, right? Then the inertia that you would have that thing. Wait, no, xi is for each of these points. Okay, okay, that's not the same thing. Oh, this is just the moment of inertia about this axis actually. Wait, okay, we are getting to somewhere. This is just the the torque, the torque on this complete thing. Oh yeah, sure. And then you also got this thing minus. So xi is common, just alpha xi summation of mi. Oh, sorry, x is common, not xi. So summation of mi xi, right? And this thing we know is just our center of mass, right? Okay, it's going to be the total mass times the center of mass, right? Okay, that guy's x value. Does that make sense? Okay, that's pretty interesting. I wonder why is that the case? The torque about this, right? That's what you look for. So, could it be that? Okay, torque about this, that would just be the torque about center of mass and then torque of the center of mass. And then similarly for this is just torque about the center of mass and torque of center of mass. But then, so the first terms are in fact the same. The second term is where the difference happens. And yeah, now I'm starting to understand what's going on. So this is the addition of like the, okay. Let's not explain that because I know what's going on and you will too when you think about it. Anyway, you got negative alpha x, the total mass of this complete thing times the x center of mass of this thing, right? So that is our torque. Now just figure it out. Okay. So alpha times inertia of this whole thing with respect to this guy, right? This is x and this will be L minus x, I guess. Okay. So you got like m L minus x squared upon 12. That's about the center of mass. Then you want to go from here to here. So this distance. Oh god, that's not nice. Maybe I should just use density. Did they write everything using what? Mass or what? Where did that go? 304 question. Steel plate. So we know the density, right? Okay, so then I'm gonna use density to that. So you know for usual, right? For a usual square rectangular plate, it's just ml squared upon 3. It's of thickness h or whatever. Okay. This is getting very weird. Anyway, so ml squared upon this is like L. Yeah. That will be your inertia or whatever this term is, right? But m is just what? M is the density times the volume, which is, oh god, this thing is L, this thing is H, and what about this thing? Let's call it as, you know what is called this as X, and this is H, oh, sorry, and this is L, right? So we should have mx squared upon 3. Then m is just rho xlh, and got x squared upon 3 is like x cubed upon 3. That's our inertia, right? And we want the difference of these two things to get this guy's inertia, right? So it's from x equal to x equal to L minus x, if that makes any sense. Okay, so it's like rho L h upon 3, and then you got what? L minus x cubed minus x cubed. I'm pretty sure the inertia has to be positive, but why does it feel like it might not be? Yeah, why does it feel like that? Oh, it's not L minus, it's L cubed. Sorry. It should have been L cubed. Okay, now it's positive for sure. Okay, that's awesome. So now we know what this first term is. It's just weird. Well, yeah, we know the first term at least. For the second term, it's the mass of this complete thing, that's the x center of mass. X center of mass will just be x plus L upon 2. Okay. And the total mass of this thing would be rho L h, and then the last dimension is L minus x. So yeah, just put that in there. And now you know the thing. So we'll have to put those. I'll just minimize it a bit. So the thing finally becomes this. You got alpha times this thing. So like alpha times what? This inertia, just put that. You know what? Just take some stuff out, like rho L h alpha. Take that out. Then you got first of all just this terms, like L cube minus x cube upon 3. Then minus of this term, so it just has L minus x as the extra thing, which is weird because that's not supposed to happen. Oh, you also have this, sorry. So you have L plus x upon 2, and you also have this x, right? Yeah. So x, L plus x, okay, I get what's happening. And then it's like L squared minus x squared, and that terms of x, of course. And all of that upon 2, right? That's what this thing will be. So it's like rho L h alpha in that times of this, which simplify it out. It's L cube upon 3 minus x cube upon 3 minus xl squared upon 2 plus x cube upon 2, right? I hope it's correct. Is this formula? It looks correct to me, right? Yeah, I mean, it does look correct. Okay, awesome. And what else was the thing? Okay, this formula is correct, and just put that over here and get this thing. You got 1 upon 3 over there, and then you got this, for which you need an x and L plus x upon 2, and you also got this L plus x. Awesome. So you finally got the thing. So you don't need this anymore. It's just this. This is our torque, right? Okay. Simplify first of all. It's just rho L h alpha times. Let's see. You know what? Just take that 1 upon 6 out. Okay. So then you got 2L cubed minus 2x cubed plus that's just 3x cubed, then minus 3xl squared. So, you know, just x cubed minus 3xl squared plus 2l cubed. That's what this thing will be, hopefully. Yeah. So that's our tau. Okay. What do you want, by the way? Oh, yeah, I just want to write that equation, right? Okay, cool. So our equation, it was, what was the thing? Our torque is just equal to IA times the Young's modulus, and that times the radius of curvature, which is just y double dash. That's our approximation, right? It is not bending all that much. For a small alpha, I don't think it won't bend. And yeah, there's also this other kind of bending which has to do with gravity, but let's assume alpha is much more than gravity. But okay, so alpha r, yeah, that's much more than g, but it's not so high that it actually bends considerably. Okay, it's kind of a weird range, but whatever. Okay, one second. What is the question? Find the deflection assuming the sagging to be small. Right, sagging to be small. That's the important part. Yeah. Of course, it's this, and then because of that, you have a deflection. Cool. So you got this equation. And once again, what's our IA? It is So usually our IA is just WHU upon 3, but in this case our W is just L. So it's like LH upon 3 Y double dash. Okay, and just put that over there. So this thing is equal to that. So what do we have? We just have rho alpha upon 2 times x cubed minus 3 L squared x plus 2 L cubed. I hope that's correct though. It might be wrong. That's what I'm afraid of, that it might just be wrong. Yeah, whatever, just keep going. And that's equal to what? So LH, that cancels, just h square over there, like YH squared Y double dash. Okay, looks good. So like Y double dash is just equal to rho alpha upon 2 Young's modulus h square, and then you got this thing, so x cubed minus 3 L squared x plus, it's not upon 3, it's upon 12. I messed up real big. It should have been times 2. Sorry for that. Oh god, this is just awful. It really looks like I might be messing up everywhere, because yeah, I'm messing up here at least. Okay, so at x equal to 0, y dash is 0 and y is 0, so that at least that's good. Cool. So it's just going to have y dash is equal to 2 rho alpha upon Young's modulus x square times x power 4 upon 4 minus 3 L squared x squared upon 2 plus 2 L cubed x, and then integrate once again. So y is equal to 2 rho alpha upon Young's modulus x square. Then you got x power 5 upon 20. Why are these weird numbers coming out of nowhere? We really did get a cubic, huh? That's interesting. I mean, it's supposed to be L squared upon 3, but then somehow this is the thing. I mean, yeah, like the mass is proportional to the length, right? And this thing is actually constant, so W is constant. Our length is what's changing, right? Okay, it works out, I think. It's not that bad. Okay, so there we go. 2 rho alpha upon x minus h square x power 5 upon 20 minus, so you got x cube upon 3, right? Okay, L squared x cube upon 2 plus L cube x square. Awesome. Yeah, that should be the thing. So take out that 20, which means it's like rho alpha upon 10 Young's modulus h square. Then you got x power 5 minus 10 L squared x cubed and plus 20 L cube x square. Okay, so that's our y value. So you want what? You want the deflection, so that will be at y is equal to L, right? Yeah. So at y equal to L, you're just gonna have the deflection, which is equal to rho alpha upon 10 Young's modulus h square. L power 5, just take that out, Okay, so L power 5 is out. It's just 1 minus 10 plus 20, which is basically 11. So there we go. It's like 11 upon 10, and yeah. So that's our final thing. Okay, so I'm just gonna wait a second. Okay, it was 304. It's just I'm really new to these kind of questions. I've never actually solved these. So yeah, sorry if I'm really slow. And when I say I'm new, I mean really new. I've never actually even got this thing till now, right? So I didn't knew about this equation, right? Tau equal to IA Young's modulus y double dash. I didn't know about it till recently, so I have zero practice on this equation. And if you want me to use it, well, yeah, I don't know how to do it correctly. But hey, at least I'm trying. Okay, 304. That's done. 305. Determine the relationship between the torque and the torsion angle for the tube. Oh God, I don't know anything about torsion. Yeah, that's like really out of syllabus for me right now. Oh, the tube whose wall thickness delta R is considerably less than the tube radius. Wall thickness and tube radius. Okay. Fine. So for that, you want a relationship between the torque and the torsion angle. I mean, we know it's supposed to be linear, but it would be better if I just find a formula for it, right? For the solid rod of circular cross section, their length L, radius R, and shear modulus G are supposed to be known. All right, so I really don't know about these kind of things. And this is like just the fifth question, and look at how many more there are. And then there's like work and whatnot. This particular question is about torsion. The next one is about power, which can be transmitted by the means of steel shaft rotating about its axis with an angular velocity. It's a length of whatever. Possible torsion angle is this thing. Oh, okay. So this next one is also about torsion. Huh. Yeah, so if I don't solve 306, I will never. Oh, 305, sorry. And 306 is also about torsion. Oh god. So I really have to do 305. Only then will I be able to solve 306 and 307. And what's 308? Uniform ring of mass M with outside radius is okay. Fitted tightly on the shaft of radius R1. The shaft is rotated about its axis with a constant angular acceleration beta. Find the moment of elastic forces in the ring as a function of the distance r from the rotational axis. Huh, that's weird. Okay, so the friction is causing it to have those forces, right? Okay, understandable. And okay, that friction is also causing like torsion of the shaft itself, but then assume it's like a very rigid shaft. And friction is friction coefficient is like infinite, so it's not slipping in any way. Yeah, it's gonna get complicated like this. Oh god. But let's try doing 305. So you want to determine the relationship between torque and the torsion angle for a tube whose wall thickness is delta R and it's considerably less than the tube radius. So when you will stretch it, what exactly is happening? Oh, you could think of each. So think about it. You got this tube. Look, I don't usually like deriving things in these videos, and because it's like really slow, right? The process is supposed to be slow and very careful, and if I try to derive it right now, I'll most likely get a wrong result, or do it in a very inefficient way, or something like that, or something which is not correct. You get the thing. But I don't have any other choice right now. I need to do this. It's just, yeah. Okay, so this is our tube, and let's just say you cut out a cross section of this thing. So it should actually be like this and like this or whatever. So you cut out a cross section. What am I doing? Just draw this as our tube. I know it's supposed to be a 3D figure, but then who cares? So this is its side view. So we will just take a cross section of this thing and now think what kind of stresses is this cross section. Okay, you know what, scrap that. What we'll do is just think about this little box. Does that make sense? So what kind of stresses does this box, okay, we should not even say it's box, it's like just a part of it. What kind of stresses does this have? Are there, so like, okay, it's front and back end, those are open to air. So there's no stress on that, right? Or if you really want, there's atmospheric pressure, but extra stress, right? That's what I'm talking about. Other than one in air, fine. So that's not there. Okay. There might be tensile stresses which are like pulling it. Okay. But do we have changing length? Not really. It's like this whole fiber, if you want to think of it. Yeah, I mean, this point is moving like that, and this point is moving like that, and this is happening. So there might be changing length, but there's like a second degree term involved in there, right? So if this was moving, this point was not moving like this, but moving like that, it had any component in that direction, this would really be much more significant than this term, right? So that's why I think this is not important, right? It might not be important. Huh, interesting. So then let's just forget about the tensile stresses because I don't think those are all that much significant. Second degree terms, right? So let's forget about that. Then what kind of other things do you have? You have shear stresses, of course. Oh God. Yeah, there's shearing. Is there like, so what was happening the last time, like compression from one side, elongation from other side, something like that? No, 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 not in this case because there is no cross-section area in the first place, right? Yeah, that's really small. So, okay, even if it is small, there might be torques, who knows? Ah, this is kind of a weird thing, huh? Like, okay, but why is there a need for that thing? So, about the cross-section, no, like by radial symmetry, we know there's not supposed to be such a thing. Or is it? Oh God. Might be like these are the okay, we'll figure it out. First, you have these. So what I'm thinking is that like this fiber of yours is bending like this and that, right? So this part, it must be being stretched like this. So there must be a force in this direction and a shear force in that direction. And of course, we need to have something that will counter this. So for that, I'm thinking there's like a force from this direction, a force from that direction. And this is produced by like, okay, these boxes. Oh, okay. These will be putting these. Okay, I'm just gonna call it like these dA values. This is area dA. Does that make sense? And then these dAs will put these forces on this area, right? And we know how this works. It doesn't create any other stress in any other direction, right? Yeah, it's just shear stress. Okay, that's awesome. So, and I could really be missing out something, but let's keep going. So there we go. This is right. You got this stress, you got that stress, and because of that, there's a change in an angle, right? Of course. So does that change in angle remain constant? Maybe, maybe not. Oh God, this looks weird. In equilibrium, there's this torque and the opposing torque, right? Okay. Uh, yeah. And is there like a differential in these two torques? Because if there's that, then why would that? Okay, there's no need for that differential. It's like the last time we saw there's a need for a differential in the torque due to normal forces because we want to account for shear force. Is this going to be happening in there that there is a difference in the torques, a big difference, right? No, there shouldn't be. Why would there be, right? Well, yeah. There doesn't need to be anything like that. Whatever torque is being produced over here, right? The same torque, the opposite of that actually, will be produced over here, I guess. So like this, right? Remember, we're taking the torque with respect to the central point, right? So that some point inside of this as an origin. So with respect to that, we're taking a torque. right? The way we are calculating is we are just taking all the forces acting on this boundary, then doing r cross f for each of these guys, and then r cross f. Yeah, right. Because of this radial symmetry, you can only care about this. Other kind of things like this, yeah, that is not important anymore because the summation of f vectors that will just be 0. So you don't have to worry about that. And this other component, so like along the force, that was not important in the first place. So okay, there's no component in the force direction, in fact. So that's not here in the first place. Fine. What I want to say is that these two torques will cancel out. So there's no difference in these torques, and that just means, yeah, the angle will remain constant. So the shear strain is constant, right? So this fiber, it will actually change like this. This angle remains constant. That's what I'm saying. Okay, so now we are ready to do this thing. Now let's, write some kind of differential equation to solve this. So how would that be? This angle, right? This angle, like how is it related exactly? You got this little thing, we call this like dx. This changes its direction, right? Yeah. So this angle, which let's just say it's gamma. So gamma dx is, yeah, now this is just getting too much. Let's go to finite case for now, and then we'll talk about the infinitesimal case. So if let's say you have this point over here and that point over here. Now, I know it's not Euclidean, but let's just assume it's actually going on a plane. Yeah, like approximately like that. So then this angle, call this angle as gamma, our shear strain, of course. And this complete length, it might just be L. So then gamma times L is this change, like, yeah. And then gamma L upon R, that's how much the angle changed. Okay, the angle when you take it subtending angle subtended on the central axis, yeah, how much that changes, right? Okay, so call this thing theta or whatever. What that means is like theta is proportional to the length. Huh, interesting. And this is the way you can calculate theta. This is just getting so complicated. Fine, so now you know that at least. Now let's go to the infinitesimal case. It's just d theta is equal to gamma dl upon r. R remains constant, right? And gamma, you can figure that out. So gamma is just the torque. This has to go through. Okay, maybe I should not say torque. Let's just say this thing is like, oh god, what's happening? Okay, let's just say this force is like F and F, and right, let's call this F. Okay, cool. It's getting pretty complicated actually. This thing is what we're calling as like dx. Okay, wow. Oh, we should really call this dx. Sorry. So, like, okay, what's the, okay, we don't actually need that dx at all. We just need the area. So area is how much for this thing? Oh, okay, it's actually depending on d theta, I would say. Not that. Just say d phi. Oh god, it's just getting so complicated. And moreover, this f is not actually f, it's like df. It's an infinitesimal quantity. Now, is that correct? Okay. Probably not the best way to be thinking about it. We want to think about torques, not this. Yeah, not this. Oh god. At least, fine, like df upon dA. That's our stress. So this is the dA I'm talking about. So df upon dA, that's our stress, right? So 1 upon g, that will be our strain. Now we just need to figure out what df upon dA is, and then you're good to go. Okay. And what's the total torque? I just want to write everything using torque. So, God, by using symmetry, we can say like this same force is actually acting everywhere, right? I mean, you got df, 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 so on. Okay, this is kind of weird. Man, how do I even use this thing to write down some stuff? All right, let's calculate a torque by doing this. So we'll just say, right, it has df upon dA thing. Oh God. Uh, how do we get the torque? Our torque will be r cross this thing, right? So it's just 1 upon g in, okay, sorry. Our torque will just be integration of, it's r everywhere. So like okay, r and then you got df, right? So this integration. Okay. Oh God. Fine, fine, fine. And because of symmetry, you can just say, okay, the torque, just because of this piece, right? Let's call this like d tau. So the r cross f value, just because of this, right? And we are only taking one phase into account because we want the torque exerted by one part on the other part. So we are only taking one phase into account, not both phases, right? Not the whole object. And yeah, it actually doesn't depend on this dx thing anymore. So just take one phase into account. It's just getting so complicated. Like, okay, integration of r df, that is tau. Okay, d tau is just equal to r df. Awesome. And what will dA be? dA is just equal to delta r times this arc length, right? Yeah, which is how much? Delta r times rd phi, where phi is like this angle and phi is based on geometry. It's not based on the deflection at all, okay? So, right, this integration is completely different than what we are doing right there. Okay, cool. So that's our dA. Now just put these over there. So df is just d tau upon r. This is going to be 1 upon g, and then you got d tau. And then what is this thing? dA. It's just this delta r times r d phi. Okay, awesome. So you got 1 upon g. This is like r squared and then delta r. Why is this weird thing going on? Oh God. R squared delta r times g. And then you got d tau upon d phi. But then remember, there's radial symmetry. So what you can do is like, in fact, just, there's like this ratio would be the same thing as the total torque upon the total angle. Total angle is of course just 2 pi. So there you go. That's the thing. Yeah, okay, that kind of makes sense. Fine. Wow, this is so much different than what I thought it would be. Right, R times df, that's what the thing. I didn't expect it to be like that. But hey, whatever. So, yeah. Man, I should really have used stress and not this df thing. Yeah, that would probably have been better. Oh God, yeah, that would have been much better, in fact. So if I just use, stress, like, okay, sigma times dA instead of df, that would have been so much better. Don't you agree? But that just defeats the whole purpose because you want to figure out what sigma actually is, depending on torque and that, right? Oh, okay. So if just for the calculation of tau, you used that thing, so like it's just integration of r then dA, which is basically this thing delta r d phi, at least that I know how it works. Like it's just equal to this thing integration of r squared delta r d phi, and then yeah, that times of sigma. If I use this equation, that would have been so much better, right? Because then tau is just equal to r squared delta r times 2 pi times sigma. So sigma is just easy to figure out instead of doing all of this. But whatever, we finally got the equation. That's what matters. It's like tau upon 2 pi r squared delta r g. This is our sigma value. Okay, so this is our what? Strain value, right? Okay, that's awesome. Right, so you got you got theta. Like, okay, differentiating that, just get d theta. Okay, that would just be equal to gamma. This thing is just equal to gamma, by the way. Okay. Then you got dx upon r. Now just put this over there. So you get d theta is equal to gamma is just this thing, tau upon 2 pi r squared delta r, then g. Starting to think that it might have been actually better to just, well, whatever. Yeah, torque is the same everywhere, right? So no, yeah, theta would not make sense in this context. In that context where you did this integral, this would have made sense, but now it doesn't because it's not changing with respect to x, that is. Okay, so d theta is this thing. That times of dx, because that's also over there, and also 1 upon r. So it should have been r cubed, it seems. Okay, that's awesome. So now we know d theta is just equal to this. It's like, okay, tau is just equal to what? It's equal to 2 pi r cubed delta r g, and then you got d theta upon dx. And yeah, assuming that the reflections are like the same everywhere, like, okay, it is, of course they are, right? But that those are not so big such that it would cause problems because of the non-Euclidean geometry this has. Yeah, assuming that happens, maybe it's not a big problem after all. Who knows? Anyway, in that case, d theta upon dx, that's just going to become theta upon L, right? Yeah, that's right. So it's just this thing, 2 pi r cubed delta r g, then you got this upon L, and that times of theta. So that's our torque. Man, that took a lot of time. Okay, I hope this is correct. Most likely it's not, but hey, we'll see. First, let's go for dimensional analysis and see if it's correct or not. So torque has units of energy. 2 pi constant. Okay, it's a pure number. We don't have to worry about that. R cubed delta R is meter cubed. So you got meter cubed. Then this thing is just pressure, right? Okay, you got pressure. Like pressure times meter square is force, and that times of meters, just force times length upon length cancels. Theta is unitless. So it's oh sorry, it was meter power 4, so it should actually be like, right, so you got meter length power 4 upon length, and then g is just pressure, right? And theta doesn't matter, it's unitless. So L cubed P, which is like, okay, P times L square is just the force times length. There we go, energy, right? So yes, dimensionally it is correct. So the only way it could go wrong is that there's factors, right? There's like more factors that I didn't consider, I guess. Like this might not be 2 pi or something else. Who knows? But yeah, let's continue. So 305A, that's the answer. If it really is correct, then man, I really actually derived everything on my own, it seems. Huh, interesting. Anyway, B. For the solid rod of circular cross section, so this was for a tube, right? Now you want a solid rod of circular cross section. The lengths L, radius R, and shear modulus G are supposed to be known. You want to figure out what relation between torque and torsion angle theta or phi or whatever. Oh, okay, they're using phi and not theta. Fine, I'm going to use phi as well. So for B, although there might be normal stress, actually no, there doesn't have to be any normal stresses. Like even if it's a solid rod and there's interactions between elements, right? So this element might interact with something in front of that and something in behind that or whatever. But in the end, the thing is like this complete curved surface is in contact with air. So, right, throughout that surface, there's no stress in the end. No normal stress, like normal to the surface, right? So that kind of stress, let's just call it like radial stress. Does that make sense? So there's no radial stress throughout this thing, I guess. Yeah, yeah. So there's only torsional stress that you have to look for. So then we can just, apply this equation for every single um, infinitesimal element like this that I will get, right? Yeah, just apply that everywhere. So then this actually just becomes, d tau, like this equation just becomes this thing. D tau is equal to, so 2 pi r cubed dr upon, the length is the same, right? Then g phi. Okay, awesome. So now I just want to integrate this thing from r is equal to 0 to capital R or whatever you want. So like tau is just equal to, I really hope I'm going correct. Yeah, let's just hope I'm going correct. Okay, 2 pi. Now integrate this thing, just r power 4 upon 4. So it's like pi upon 2. Okay, pi r power 4 upon 2 L G phi whatever, and it goes from r equal to 0 to r. So yeah, this is the same thing as that. So there we go. That's the thing, right? Okay, so you got tau for this thing. I mean, like hopefully it's correct. Mostly it's not. Yeah. Next question. But if this is the correct thing, then this is also correct, right? Okay. 306. Calculate a torque twisting a steel tube of length L equal to 3 meters through an angle about its axis if the inside and outside diameter of the tube are equal to D1 and D2. Oh, so it's like the last question, except a little different, right? Steel tube through some angle. Interesting. Yeah, okay. All we will need is, where is the Young's modulus? No, okay, we don't need a Young's modulus, it's shear modulus that we need, of course. Sorry. Yeah, for a second I thought there's no modulus of elasticity. What's going wrong? There is, of course, that. Okay. So yeah, the same as the last question, except that you're just integrating from R1 to R2 and not from 0 to R. So yeah, like the torque will just be equal to what? Pi g phi upon 2L, and then you got what? R2 power 4 minus R1 power 4. Okay, awesome. Next question. I won't calculate because I don't know the G for steel. Okay, next. Find the maximum power which can be transmitted by the means of steel shaft rotating about its axis with an angular velocity something. If its length is okay, LR are given and the permissible torsion angle is this thing. So you want the power that can be transmitted. God. Like okay, I get there's a torque on whatever body the rod will be attached to. But how do you get the power? Usually we just like F times dx. So torque times d theta. That's right. I guess so. Like okay, half I omega square is the kinetic energy. Just differentiate this thing. So it's just like I omega alpha. That's not what exactly is supposed to happen. Oh, okay. I alpha. Oh, that's like the power. Yeah, this is the power, of course. I alpha is just the torque, and then you want this times omega. So that's our power, of course. So omega we know, right? Torque we can figure out. Huh. Okay. And you also kind of know what phi is. So torque is just this thing, like, okay, put that in there. Steel shaft, so it's a solid rod, right? Then just use this formula. And once you use that, just multiply by omega, and there you go, you got the power, right? So it's just going to be what? This thing, of course. Next question. Wow. Just next question. That's the power, right? I hope so. I mean, once again, look, you didn't give me what G value is. So yeah, 308. A uniform ring of mass M with the outside radius R2 is fitted tightly on the shaft of radius R1. The shaft is rotated about its axis with a constant angular acceleration beta. All right, it's that question. Find the moment of elastic forces in the ring as a function of the distance r from the rotation axis. Wait, what? Isn't r the same? Oh, why is this a ring in that case? You say it's a ring, but then it has inner outer radius. It should be like, if it's a ring, it's not supposed to have two radii. Huh. Okay, whatever. The shaft is treat about the axis with the constant angular acceleration beta. Find the moment of elastic forces in the ring as a function of distance r from the rotation axis. So the ring can be thought of as like this case actually, right? Yeah, yeah, that's right. That's right. So before anything, the ring was like this. Exactly. Oh, it's like having some kind of angular acceleration, huh? It's just getting so complicated actually. Sure, you're rotating it like that. I get it. Ah, now something's just going wrong. Do we not take into account the density and everything of the ring? I mean, we should. Otherwise, oh God. Mass M. Mm-hmm. This is very weird. Like, I get it's like a very. I mean, okay, so this was your radius before doing anything, but then after this started to accelerate, it's actually going to go like this, right? This part, so this point will actually shift like that, and this point is still there because friction, right? Okay, and this angle is our phi. No, not exactly. uh that's not phi. No, 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 this is not right. Oof. Oh, I see what's the problem. The last time we did that phi stuff, so yeah, it was based on this thing, right? Yeah, okay, this was, so the tube whose wall thickness delta R is considerably less than its tube radius, fine. And then, okay, the torque and torsion. No, 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 it's a completely different thing that we're doing right now. That case, in that case, what was happening was, you need to think of it like three-dimensionally. It's actually this part which is staying just like that, and then this part is rotating, right? In this case, that's not happening. In this case, this part is also rotating. Okay. Oh, God. Now, that's just not good. Uh, what was the question? 308, right? Yeah. Okay, it's a completely different case, so we will need a different approach. And how do I think of it? Once again, just use element analysis. So I'm thinking of an element. in this area, right? Okay. Should I think of it like a square or something else? Maybe I should think of it as like this. So it's an area element like this. This is like dr, this is rd, you get the thing. So when it starts rotating, what exactly is happening over here? To keep this whole thing, okay, like not exactly just this thing, but this whole thing, in fact. So everything um outside of this circle, that has to be rotating, right? So yeah, for that you need some torque, and that torque is produced by friction or something like elastic forces. Yeah. So like for this case, when it's in contact with this other thing, it's friction, but then over here it's like the elastic force. That elastic force, uh, right? uh God. So because of that elastic, like it has to be in this direction. Sure, 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 sure. That kind of makes sense, huh? Damn, even writing a single differential equation is kind of hard for this one. So okay, that shearing force, we'll just say it's the same everywhere and it's tangential to the, sorry, it's parallel to the surface and it's the same magnitude everywhere by symmetry. So with that, can we figure out what that's going to be? For some certain alpha, you can actually figure out what the torque on this thing is going to be. It's not that hard. Okay. Right. So how much is it, by the way? What's the torque on this? Uh, yeah, I mean, like, okay, we should actually do it correctly. It's 308. It's a uniform ring of mass m. They didn't give us what material it's made of. Find the moment of elastic forces in the ring as a function of the distance. Wait, what? Wait, this is just stupid. This is just stupid because they didn't actually give us the material and they don't even want us to figure out the strain and whatnot. They just want the torque because of these elastic forces, which is so element. I mean, it's just the torque on this outside stuff, right? That's not a big deal. We can actually do it. Oh, okay, okay. I get it. Right. So yeah, find that torque. No big deal. It is the inertia about the axis times alpha. So tau equal to I alpha because it's x asymmetric. So you can use that. And I'm using this not for the complete ring. I'm just using for a part of the part outside a certain R value. Okay. So what's the I going to be? It's just going to be, okay, like for that kind of thing. It's proportional to what? So we know it's just mr squared upon 2 for a complete solid cylinder. Now for like, okay, a cylinder minus a smaller cylinder, how would it be? The the volume of the cylinder is proportional to r squared. So you're gonna have that r squared in the denominator. And then for dimension analysis, it's gonna be r power 4, but both of it is like delta of these guys. Now it's like 4 r power 3 dr if I go into differentials, and that's like 2r. So okay, you're gonna have extra 2 over there, so it has to be mr. Wow, it's getting complicated. Just m, and then you got all of this stuff, and it should be upon 8, I think. No, not 8, actually it's 4. Yeah, m upon 4 in this thing, right? Oh god. No. It's just m upon, sorry. Like m upon 2 r2 power 4 minus r1 power 4 upon r 2 power 2 minus r1 power 2, right? That's the thing. So this formula, if you don't know where it comes from, watch that video where I told you about a lot of different moment of inertia, right, for different cases. So one of the cases has this formula. Fine. Right. So just a quick check. When r1 equal to 0, this just becomes what, like m upon 2 r squared, which is exactly what we want. And when r1 r2 approach each other, it just becomes mr squared, right? Yeah, which is the case of just a ring with no thickness, right? Yeah, there we go. So you got inertia of that thing and then use of alpha just now. What kind of question was this? Huh, interesting. It's just this. It's just this thing. So it's like m alpha upon 2 delta r power 4 upon delta r squared. That's our answer. Next question. And hey, they gave us values. No, they didn't actually give us values. But whatever. And actually, I should write it correctly. So outer radius is what? Outer radius is like R2. Okay. Uh-oh. Shit. The mass I'm talking about is not the mass of the complete ring. Then this is not the formula. Oh. Huh. That is not good. And you wanted a certain R value, right? Mm-hmm. So yeah, it's this thing m upon 2 alpha r power 4 delta of that r2 power r2, sorry. But then the mass that we actually look for, that's not this thing. So let's just call this like capital M for now. So capital M is the mass of the outer stuff, which is how much, like in proportion to the complete mass, right? Yeah, that's our answer. That's going to be the thing. So like M upon M. I just told you it's proportional to R squared. So this is actually going to be what? It's supposed to be R2 squared minus R squared upon R2 square minus R1 square. That's better. So like M is just equal to this thing. Just put that in there. Yeah, just put that in there. Some stuff will cancel out, I guess. It's just M alpha upon 2 R2 power 4 minus R power 4 upon R2 power 4 minus R1 power, sorry, R2 power 2 minus R1 power 2. Good. Next question. Okay. Next is 309. 309 is finely elastic deformation energy of a steel rod of mass something stretched to a tensile strain. Okay. Deformation energy of a steel rod of mass something stretched to a tensile strain of epsilon equal to 10 power negative 3. Huh. Well, no, it's not that bad, I guess. It just stretched. I don't see how mass is important. Oh, okay, so the mass is important because you need to know how much of steel was there. So what was the thing once again? Like, yeah, the volumetric energy, that was just equal to half stress times strain, which is like half Young's modulus times strain squared, right? Of course. Right. So you just want this times the volume of steel, which is just its mass upon the density. There you go. That's your answer, I guess. Yeah, awesome. And now it's time for actually deriving this thing because I don't like to present you with formulae that I have not used myself. Okay. Like you just have this rod and so our energy put into this thing is just equal to integration of so just say it's like area A and this length is L, right? So this will just be the force that we are putting on this rod to stretch it, yeah. So we're putting like F from this side, F from that side, but in the end, like it stretched by delta L, delta L. Let's just let us delta L upon 2, delta L upon 2, right? Delta L upon 2, this move, and delta L upon 2, this move, right? So in the end, no matter how you distribute it, it's only like F times of L. That's the energy that we put into this thing. What is F, by the way? So for reversibility, right, you would just want this thing, our F, to be equal to the stress in this rod times the area, which is the Young's modulus times the strain times the area. Okay, and that times of um, dl, right? Okay, so like, yeah, awesome. Yeah, that's right. Okay. Uh, but remember, like dl is actually just the length times the change in strain, right? Yeah, sure, sure, right. Like dl upon l is by definition the change in strength. So the strain is just like, okay, the change in strain is just equal to dl upon l, or I should say dl is equal to lde, right? So then this whole thing is just the Young's modulus times this thing is just the volume of this thing. And then you got integration of epsilon d epsilon, or whatever this symbol is. And yeah, there you go, like half Young's modulus volume epsilon naught squared. So it goes from 0 to something. So that's the energy spent into deforming it, right? I guess it also needs Poisson's ratio or something. No, it doesn't. It doesn't, because area doesn't change. So it doesn't, right? The volume also doesn't change all that much. Neither does the area. So yeah, this is actually correct. Doesn't require Poisson's ratio. There you go. That's the formula. Yeah, so like that's the thing. And now volume is just the mass upon the density. So there you go. This is the formula that we got last time. Okay, this is like, both are just strains. I'm using them interchangeably. Whatever. Okay, next question. 310, which is a steel cylindrical rod of length L and radius R is subjected by its ends, suspended from suspended by its end from the ceiling. Okay, find the elastic deformation energy of the rod and define U in terms of tensile strain delta L upon L of the rod. Oh, okay, cool. So you want to find deformation energy of the rod? Oh god, it's gonna take forever. Whatever, let's do the thing. So I'll just gonna figure out what the strain is at different x values. So this is the thing. Let's just say this is x equal to 0, right? So this is x equal to what? How long is the rod? Length L and radius R. Okay. Let's say it has area of cross section A, which is like pi r square, but whatever. And at some x value, what is our strain going to be? What's the stress, by the way? Like, okay, the stress times the area, that is equal to force, which is pulling all of this up, right? Which is just the density times the area times this length, which is just x. So the stress is just equal to rho x. Okay, which means our strain is just equal to rho x upon, or you know what, let me just leave it like that, because yeah, okay, yeah, it's good enough, whatever. So this is our stress at some x value, right? Awesome. Uh, yeah. Wait, one second. What did you want, by the way? Find. Okay, which question was this thing? 310. Find the elastic deformation energy of the rod. Okay, so if that's only what you want, I can do it. I thought they would ask like find the actual change in energy, which would have to do with gravitational change in energy as well. So yeah. Anyway, if it's just the elastic energy, then I know how to do it. So sigma equal to rho x at some certain x value. So our um, energies, volumetric energy is just going to be what? 1 upon 2 sigma squared upon the Young's modulus, right? Yeah, or you can just say sigma squared upon 2 Young's modulus. That's the thing. Now, sigma is just this thing, so just equal to what? Rho square x square upon 2 Young's modulus. This is the volumetric energy. Now, this times the volume itself, which is this just the area times dx. So that's the energy stored. Just want to integrate this thing, right? Easy as that. It's like rho x cubed a upon 6 Young's modulus, and goes from x equal to 0 to L. So there we go. It is this thing. So yeah, I guess that's right. Oh, sorry. It's supposed to be L over here. Yep, that's the energy. That's the U, huh? Okay, so U is just equal to, this was the A thing, is equal to rho L cubed. A is just pi r squared, by the way, upon 6 Young's modulus. Now they want me to express this using what? Oh yeah, using dl upon L, right? Okay, that is using the net tensile strain. Yeah. So you know what the strain is? I mean, the strain is just equal to rho x upon the Young's modulus. So then this times dx is the change in length, right? If you just integrate this and then you just get the thing, right? It's just going to be like a rho x squared upon 2 Young's modulus from 0 to L. That is just equal to like, okay, rho L squared upon 2 Young's modulus. Yeah, I guess that's the thing. Now, this upon the original length, which is L. So this is the thing, rho L upon 2 Young's modulus. That's the strain, the actual strain. So that's dl upon L. Huh. It's funny how this rho comes out of nowhere. Uh-oh, I'm missing a factor. Right, I'm missing this factor everywhere. Uh-oh. This isn't nice. How could I miss that everywhere? You want to have g squared, g squared. This should also have g squared. So I need this over here as well. So yeah, integrating that, just get this extra factor of g over there. Yep, it's supposed to be there. So then this thing is the final thing, right? Like rho LG, doesn't that look familiar? It's like saying Young's modulus times dl upon L, just like the effective stress is just equal to rho LG upon 2, right? Which is making sense because like effective force, if you want to, that will just be equal to, in that case, rho AL G upon 2, which is like rho V G upon 2, it's like M G upon 2, which makes sense. So yeah, it's like average stress, which I've always told you about. So yeah, you want this using dl upon L. I'm gonna give you it. I'm gonna give you the thing. So we don't know what. Wait, which dimension do we not know, by the way? I think we don't know what the length is or something like that. Okay, then the length is just equal to, let's call it like E, let's call it like capital E. No, we only have capital E for energy. So, right, this is actually good enough. This symbol, effective, if I want, I'm gonna add a subscript of effective. So L is just equal to 2 Young's modulus E effective upon rho and G. Now just put that in this thing and you'll get the thing. I don't get it. I want to express it using that, but which of these do I want to eliminate? I don't know. I mean, they give us length L and radius R. So what else is there that, oh, they don't want us to use the density and Young's modulus. Right. I think that's what they are doing. Okay, that's understandable. So just, yeah, like density upon Young's modulus, just don't use that. Right? Times G as well, in fact. Huh, isn't that obvious? This is just equal to like 2 effective strain upon the length. Okay, and where did that go? What did we want? We want the energy, which is this thing. So rho upon Young's modulus, and then another G over there as well. Just put that over there. You know what? Just put another 2. So, You got 3 in the denominator, and then also like L. Okay, 3L. Then you got E effective. You took rho and G and Young's modulus. Yeah, so that 2. Okay. So there's a G remaining as L cubed. That's remaining pi R squared remaining. This cancels just L squared. It's just E effective times L squared pi R squared G upon 3. Okay, awesome. That's the thing. What I think it is. Fine. Next question. Oh, this was B actually, not A. So this is B. Okay, next question. 311. What work has to be performed to make a hoop out of steel band of length something, width something, thickness something? The process is assumed to proceed within the elasticity range of the material. What do you mean you want to make a hoop? Huh? Oh, so you like want to bend it. You want to bend it and then make a hoop out of it. That's pretty weird. Okay, so what work has to be performed to do that? I get it. They just want us to figure out a change in elastic potential energy, but then is that actually the work? Maybe it is. Who knows? Right? Maybe it is. Yeah, just figure out the. Oh no! Oh no! This is a problematic thing because the strain. Oh, it's really unfortunate, isn't it? So I think that's not the way they want us to do it. Huh? Some other way of doing it. Like using units of coordinates or something like that. That goes to infinity, then it's supposed to come closer and closer and then. What's the work required to change the radius of curvature? I mean, you know how much torque is required to keep the radius of curvature like that. Okay, and it's just pure bending that we're doing, nothing else, I guess. Okay, cool. But what's the amount of work required to change it? Now, this is getting complicated. Man, I really don't know. How would you change it? Um, okay, I'm running out of ideas. Come on, think about it. Hoop out of steel band. Oh, okay, I got the setup for this. I think this might be the thing that we should be doing. So here's a sphere on which I will put my already deformed hoop. Okay. So I know they want us to make a hoop out of the rod. I'm gonna make a rod out of the hoop, if that makes any sense. The only reason I'm doing this is because okay, maybe that's not the way it should be. Uh, then how would I do it? Come on, think about it. Okay, so what about if I don't put this on the sphere, instead put it inside the sphere? So here's the sphere and here's our rod. So yeah, like this rod is inside of the sphere and like this, and this R is a variable quantity. We can change the R value, right? So the sphere can become bigger or smaller depending on how we want this to happen. I know it's very unrealistic, but then yeah, just think about it. If we had something like that, it would be perfect, right? Okay, and then this is just so stupid. Yeah, the real thing would be like you would actually produce torques at these 2 points and then bend it, right? And this is like so much different than that. God. But I want some uniform way of doing this. This is probably the best way I can do it. Okay. So what we are doing is we are making its radius of curvature smaller. So we are, yeah, decreasing the radius of this sphere. In doing so, this angle increases because this guy's length is almost constant, sure. And we just want to figure out, yeah, right, like how much work do we have to do? Okay, I'm starting to have second thoughts about it. Maybe it's not the best to do it like this. So what other way can we do it? Okay, any other way of doing it? 311. The whole problem with this, with the volumetric energy and all that, is that you will actually have to go, to the cross section to see what's happening, because the stress is different everywhere. That's not something I want to do. Oh God. Yeah, we don't have any better choice. So just go through that. Fine, fine. So what was the thing? Once again, you had this neutral line. Then this is your element. Okay, this was our neutral line. This is our radius of curvature. Okay. This line, this fiber, it didn't actually have any change in its length at all, but these things did. So how much was that, right? Let's just say this is the positive y value. Then the strain at some y, what's that going to be? Just going to be like y times theta, right? Of course, that's okay, y times theta upon r times theta. So just wait, what? No, y times, okay, y upon r, that's better. So, like that's just, this angle is just theta, called like 2 alpha or whatever. So this angle is alpha, this angle is alpha. Then this angle is alpha, or this angle is alpha over there. So then this is just y times alpha. This length is y times alpha as well. So combined just y times theta, that's the increase in length, and that upon the original length, which is just the same as this length, which is actually just r times theta. So that's why it's y upon r. So y upon r is the strain. Well, this is interesting how it doesn't actually depend on theta, which is okay. It's obvious because r is directly dependent on theta. So cool. Like, okay, y upon r, that's the strain at that point. So, like half Young's modulus, this thing squared, that's the energy density, right, for the y level. What is the area of that y level? What kind of shape was this once again? It's a steel rod. Oof. A rod. That's not what I want. Oh God. It's a rod. That is not good. If it was like a prism, or okay, if it was like a cuboid, a very thin cuboid or something like that, so a wire with a square base or something like that, right? It would be so much better, but it's a rod. Now I'm gonna view the cross section from this side, right? It will look like this. This dA element, it's at some y value, okay? Yeah, and then the actual volume that we will have is not, yeah, okay, the volume will just be dA times the length for this goes, which is like this 2 pi r. The 2 pi r thing is like there throughout. So 2 pi capital R, right? It's going to have pi capital R Young's modulus y squared upon R squared, and that times this dA. So this thing is actually energy, right? Okay. Simplify first of all, just pi Young's modulus upon radius y squared dA. So hey, somehow it turns out like, oh, this is weird. Like, yeah, this is seriously very weird. So this also involves um, our aerial inertia. Huh, interesting. That's the energy. Now you would like to integrate this thing, right? Okay, so pi Young's modulus upon R and then I sub A. That's the final energy that you will have. Is this dimensionally correct? Young's modulus times this things like, okay, that is y squared dA is, so dA is already area that times of length squared. So this part is that's just force, right? So this part is, so meter square upon meter is just meter, force times length, that is energy. So yes, dimensionally it's correct. So I think this is the answer. Huh, whatever. Right, so that's the energy, or I think so. Once again, what is the symbol for it? Wait, it's a steel band. So then where was the steel rod? Did I just... Steel band, right? It's not a steel rod. I... Where did I read steel rod? Oh, so 312 has a steel rod. Oh. Huh. Oh. And this is actually steel band. So there was no need for this thing. Just use IA equal to WH cube upon 12 once again. And then there you go. That's our formula, right? Okay. At least we have a general formula now. So the energy is just this thing. See, that's why I don't use E for Young's modulus, because okay, let's just use U because I want to stick to their terminology for a while. It's just this thing, pi Young's modulus, inertial, inertia of area, aerial inertia, yeah, and then 1 upon R. Okay, this is in red. Awesome. And now let's do 311. Now that we know this, you know what, actually this was a part of 311 anyway. Okay, what is the answer for 312? So for 311, our IA value, since it's a steel band and it's not like a rod, our IA value is just like pi Young's modulus. Wait, what was it once again? Length is given, width. Oh, it was not 2 pi. Oh God. And it was not supposed to be 2 pi. That angle is not the length that we had. That was not supposed to be 2 pi r. It's supposed to be different, right? Oh God. Oh God. This is for making a complete hoop, which is of course going to be of a particular radius. So no, we don't want this. We actually want this thing, theta upon 2. That's better. Of course, that's much better. Now we can do it. Okay, and what is theta, by the way? Just equal to L times R. So yeah, sorry, L upon R. So this actually is just this. Yeah, this is like a much better thing. Finally, we have a working formula. So now let's do it. The length is 2 height. So okay, width, right? So that's what we are calling W. No. And thickness, okay, so this thing is W and that is H, just H. Understandable? Wait a second, the width. What is the width actually? Oh god. When they said this is like thickness, what does it actually mean? I'm trying to think that is maybe not the weight should be 6 centimeters. Isn't thickness like the difference of radii? So outer radii minus inner radii all the time, which would mean that this del is what we actually usually refer to as h in our formula for WH 2.12, and this thing is in fact W. Oh, okay. So in this case, you would just have h del, okay, del cube upon 12 as our IA value. Just put that in there. You get the thing. So it is L Young's modulus h del cubed upon 24R squared. Right, that's our answer, I think. Okay, this is the formula that we use to get this answer. Now let's go to 312. Find elastic deformation energy of a steel rod whose end is fixed and the other end is twisted through an angle something. Oh god. The length of the rod is equal to this and the radius is equal to that. Okay, I get what they're going for. So our torque is just this, right? Of course. And then, yeah, like torque times d theta, that so tau d theta is equal to the work done, right? So you just want to integrate this thing. So basically what you will get is like pi r power 4 upon 4 L and that of G. This is the energy that you will get, right? Or something. Oh, it also have like phi squared, sorry. So yeah, that should do it. So this is the work done by us. So which of these things do we know? We know G, we know pi, we know R as well, and we know L. So perfect. But I won't work out the work out the value because I don't know what actually G is in numbers. Anyway, this is this thing pi r power 4 G phi squared upon 4L. Hopefully that's the thing. Now 313. Find how the volume density of the elastic deformation energy is distributed in a steel rod. What? Volume density of deformation energy is distributed in the steel rod. Depending on the distance r from this axis, length of the rod is equal to L. The torsion angle is equal to phi. Oh, hey, I know a way to do this. I think I do. So you can think of, so this is the rod, the cross section of the rod, and then, okay, we know this, like this part, so the other face of the rod, it doesn't rotate. This rotates by some kind of angle, phi, right? So you can think of this rod as being made of, you know, like these two parts. So another rod, right? So it contains this rod, right? And then you have this part. So you know what's the energy required to twist a rod, right? And we know this rod inside is also twisted by the same angle phi. Just that its radius is different, but all of the other things, right? Those are the same. The phi value is the same, L is same, G is same, right? It's only that R is different. So why don't we just like use this formula for this rod, right? Yeah, that will give us the energy required to twist this thing, which is like the energy stored in this twisted part, if that makes sense. And then the differential of that energy as we go outside, like, yeah, so d upon dr of that. Okay, not dr. Upon dv, which is like d upon dr, but then you have an extra factor of 1 upon the this area, right, the CSA, which is just 2 pi RL, right? So what we want is like 1 upon 2 pi RL, okay? And d upon dr of the stored energy inside of this rod, right? Which is a function of r, by the way. And yeah, u is just this thing actually. So when we use this, we'll actually get the energy density in this region, right? Yeah, isn't that just awesome? It looks awesome, I think. Okay, let's just use the thing. So you will have pi r cubed g phi squared upon L for our derivative, and then you got this thing. So like 2 pi r L. Pi cancels, just get like r squared g phi squared upon 2 L squared. That's the energy density. Oh yeah, yeah. There we go. Next question. So what does it say? It says that when your length is bigger, it is easier to, like, because the energy needs to be okay. No, it's probably not like that. That probably relies. So okay, that probably is related to the actual torque, right? And not the, yeah. So how difficult is it is to bend, right? If you have ever done this in life, that you have like, I don't know if you actually have something like that. So you took something that is something like a steel rod and then you just try to bend it. Yeah, what you will feel is that it actually, like, yeah, you have to put more torque as the deformation gets bigger, right? So first it's like, it's hard, it's still hard to bend it, but then it's actually easier than afterwards, right? So afterward, even keeping it like that requires some push, right? So I think, yeah, that's related to torque. It's not related to the energy density. No, that is completely different. You can't make any physical sense of it, I think. Just if we could, that would justify this. But hey, whatever. And also it says that bigger R values means more energy. I guess there might be some truth to it. Because the bigger R values, those will have like more mass, first of all. And also I think the shearing is more in those bigger R areas, right? Yes. Anyway, 314. The only thing I'm worried about is what if there's um, some numeric factor that I'm missing out, right? Otherwise, this looks good. Okay, 314. Find the volume density of the elastic deformation energy in fresh water at the depth of h is equal to something. What? Volume density of the elastic deformation energy in fresh water. Oh god. This is very weird. In fresh water, huh? The work done by fresh water is also supposed to be accounted for, right? Yeah, I get it. I get what's supposed to happen, right? It's just that uh, we know Young's modulus is pressure dependent, right? I mean, the effective Young's modulus, the one that you will actually measure, right? It's dependent on the pressure. So, which Young's modulus are we actually using? Yeah, that's the thing. Which of them are actually using? Interesting. Well, whatever. Let's try to do it. So, what do we have? The work done by us, that's just equal to FTL. The work done by water is, so yeah, like its volume is actually increasing, or okay, dV is for increase, so negative PdV is the work done by that. Hey, we are also doing negative work, right? No, we are doing positive work. We are doing positive work because the contact point is moving with the force F, right? Not opposite to it. And for water, if its volume increases, then negative work is being done by water on this thing. Otherwise, it's like positive. Yeah. So it overall just like negative PdV. So P is the gauge pressure of the water because yeah, like the Young's modulus that we'll measure is probably one that you will do in, you know, like what do we call it? In the in atmosphere, not underwater, right? I think. Wow, it's just getting so complicated. Wait, okay, this might just be that this question is actually, oh, it might actually be different than what I thought it is. Because they didn't actually give us anything about the strain or whatever, right? So if they would want us to do the work on the metal block, they would have given us still what strain do you have to pull it, and that's gonna give you the volume density, right? So without specifying that, I don't think it's correct to answer this because then you will have to explain what strain is. So I think this question is related to not us pulling on the block. It's like the how do we call it? It's water doing work the on the metal block or whatever, which compresses the thing. And once that happens, right? Okay, it's starting to make sense now. Yeah. So then it's just going to be like what? Um, it's like half bulk modulus and then the strain, the volumetric strain squared, right? Because PdV, it's hard to express what's supposed to happen. So it's like PdV is the thing, right? You want this integral or negative PdV or whatever. Hey, but the pressure. Okay, this is getting complicated. Right. I mean, when you actually, yeah, what water is doing is not at all reversible. We want a reversible process, right? So, um, yeah, like just make P be equal to, it's just not making sense anymore. We want negative PdV. Now we know that dV upon V times the bulk modulus, this is just equal to affinity of that thing. This is just equal to the pressure, right? Or I should say like dP. Yeah, that's better. So what does that actually mean? dV is just equal to negative dP times volume upon the bulk modulus. The whole problem is of this volume. How am I supposed to use that? How am I supposed to get the pressure by itself? Yeah, that's another problem. I get it, the volume barely changes. So this is just equal to this, like negative integration of PV upon P. Right, okay, PV upon P, and then you got T. Well, that negative just changes. So it's this thing, I get it. But can you just ignore the fact that volume is in fact changing? I don't think so. But hey, whatever, just integrate this thing. And unfortunately, it's not like the changes are related, not the quantities themselves. It's not like stress strain anymore. So it's so much harder to do. I get it. Anyway, it will just be like what? Half volume p square upon the bulk modulus. Yeah, that is the thing. Sure. It looks about right. Looks about right. PV is just work. So yeah, and that just means like half P squared upon B or P squared upon 2B. This is really just the volumetric density, right? Yeah, that is assuming the volume doesn't change all that much. And I think it's an okay assumption to make, not that bad. Fine. So then that's the volumetric density for whatever material you put inside of water or inside of anything which has a pressure more than the atmospheric pressure, right? Or less or whatever. Hey, what if like you measure every Young's modulus in vacuum? Yeah, that would like give you a base value, and then you would have just half p squared upon b actually, right? And yeah, that would be so much better. But now what you actually have to do is like half, so 1 upon 2b, and then you got this thing p squared minus p naught squared. That's the energy that you had to put into this thing, right? This is very weird. When we said energy density, what are we taking as our zero value? Where is the reference line? To what do I compare? What's my zero? I would say zero is when you have vacuum, right? Yeah, that would be the thing. I think so. But if you just want the zero value bit to be like at P naught, then fine. This is the energy density in that case. Like P square minus P naught squared upon 2B. Now I'm still gonna use this as the energy density. Yeah, because this just fits better. So yeah. And now P is not gauge pressure. Awesome. It's like P squared upon 2B. And B is of course the bulk modulus of whatever material you put in water. So yeah, that's it. Next, you will be doing hydrodynamics. Okay. Hey. Yeah, okay, I know this one. I also know this one. I do know this one. Yes, I know that one as well. Ideal fluid, okay. So it's like Eulerian equation. I don't know what this is. What is this? Rho dV upon dt is equal to what is this thing? Volume density of mass forces. Okay, this is new. I don't know what this is. I do know all of these things. Stokes law, Poisson's, sorry, God, how to pronounce this thing? Poisson's law, whatever. This equation, which is basically like about resistance of tubes, so like fluid resistance. Okay, yeah. Yeah, I know these things, but what is this new equation? I don't know. And you know what happens when I don't know something? I'm gonna need some time to do this. Okay, how many questions? So it starts off at 17. Okay, not 17. 15, 315, and it goes till 339. And wow, would you look at that? Are you serious? Why? Why do you want me to do this? It's not even in my... I'm not gonna do that, okay? I'm just not going to do that. Oh God. Yeah, okay, fine. I'll just do hydrodynamics in the next video, and then I'll just quit it because now it's getting out of syllabus. Who in their right mind would do this? I mean, okay, I would if this was before this crucial time period of my life. I would have done this. But now I can't. I don't think it's worth to do. Anyway, I'll see you guys in the next video.